We're going to look at a typical optimization problem. So an optimization problem normally is basically when we're using differentiation to find a local minimum or a maximum in order to give us sort of the optimal conditions on some kind of problem. So, for example, here we've got the cost, which is C, of ordering and storing X units of a product, is given by the function C in terms of X equals X plus 10,000 over X. A delivery truck can deliver at most 200 units per order. Find the order size that will minimize the cost. So we're going to assume this is a non-calculator question, but it still might, is interesting to look at what the function looks like, so we get an idea of what we're trying to find. Okay, obviously we wouldn't be able to do this in a non-calculator exam, but if you graph the function, there it is on GeoGebra. Now I've blanked out the scale on the x and the y axis because I don't want to give away the answer before we start, but basically this is the point that we're looking for, and what we're looking for is what's the x value here. Let's make a start. Basically, if we differentiate first, the first derivative is going to be 1 plus, now it's probably useful to write this as x plus 10,000 x to the negative 1. Excuse the noise in the background. So it's minus 10,000 x to the negative 2. That is just a toddler having a tantrum in the background. She's not being murdered or anything. She just probably doesn't want to go to bed. Okay, so we've got 1 minus 10,000 x to the negative 2. And we've got to let that equal to 0. So I'm going to write that without the negative indices. So basically it's 1 minus 10,000 over x squared equals to 0. So 1 equals 10,000 over x squared multiplied by x squared equals 10,000, and actually it's a nice simple x is plus or minus 100. Now you're not going to have, in most optimization practical problems, you're not going to be able to have a negative value of x if it's time or number of products or whatever, or number of storage units. So you can't have negative storage units. So you might want to just acknowledge that x cannot equal to negative 100. So we conclude x equals 100. Now, there's a lot that this question didn't ask. Okay, it's possible that you need to prove that this is the minimum value and not the maximum value. We can see from the graph that it is the minimum value, and if I just get rid of that, you can see that there we go. It was at 100. Okay, so it might have asked to prove it's a minimum. So to prove it's a minimum value, we just take the second derivative. The 1 disappears, and we've got negative 2 times negative, so we've got plus 2 times 10,000, so we've got 20,000 x to the negative 3. And if we plug in 100 at that point, we've got 20,000 over 100 cubed. Well, you could work all that, what that is. You're going to have a million, 20,000 over a million. Oops, there. But it doesn't really matter. The key thing is you can see that that's positive. It's a small positive number. So it is a minimum value. The other thing, obviously, that wasn't asked was, what's this value? What's the actual cost at that point? So the cost, we don't even know if it's in dollars or pounds or anything, but we'll just assume it's in euros. So the cost is 100 plus 10,000 over 100, over 100, which is 100 plus 100, 200. Okay, so everything that we're getting from our differentiation matches with what we've got from GeoGebra. And okay, so we'll stop there. By the way, if you're worried about the toddler in the background, she is fine. She's not choking. She's just putting it on to try and get attention, and her mum is with her. So, she's fine. Don't worry about it.